Good afternoon, everyone. Welcome to my talk. This is one of the last two sessions of this conference, so probably you are already tired a little bit, so I hope you enjoy this session. Today we are going to take a look at how we evolve the core replication protocols of Hazelcast. I am Ensar Basri Kahveci. I live in Ankara and I work at Hazelcast as a distributed systems engineer. I would like to start with a question. Can you please raise your arm if you are familiar with Hazelcast, using it, evaluated it, checked the documentation, etc.? Nope? Okay. Hazelcast is the leading open source in-memory data grid written in Java. It's like a key value store. In simple words, it's a data structure cluster that works in memory. And it gives you distributed implementations of Java collections APIs like map, set, queue, list, and also concurrency APIs like logs, atomic longs, atomic references, countdown latches, etc. And besides data storage, it also gives you computation, processing, and messaging features like distributed executors, scheduled executors, topics, and stuff like that. So it is a data grid, and data grids are mostly used for distributed caching and keeping data in local JVM for fast access. And they offer elasticity, availability, high throughput, and low latency for data access. And they work in memory by default and keep multiple copies of data to tolerate failure. So they can be considered as distributed data stores. And to meet with these design goals, they make use of different techniques, replication techniques under the hood. And in this talk, we are going to take a look at these techniques from the perspective of Hazelcast. Okay, let's start with defining what replication is. So replication is the technique of keeping multiple copies of a data set in different places. We call each copy a replica. And replicas can be processes in a single server or in different servers in the same data center, or maybe in different data centers, or even across different continents. And we make use of this technique because, for instance, we may require to tolerate failures and remain available. We may require to reduce latency by talking to a closer replica of our data set, or we may require to increase throughput of our system. And if we have an immutable data set, things are relatively easier. But replicating mutable data sets, or in better words, mutating replicated data sets involves several challenges. We need to answer a lot of questions like how can we keep our data replicas sync with each other, how to handle concurrent read and write operations on different copies, in a way confirming to our consistency model, or on which replicas we should perform these read and write operations, or how to handle failures. What if there's a failure while we are just trying to update a copy or a replica? So, and we cannot have a single solution that will cover all of these questions in the best, or in the optimal way. We always make trade-offs while designing replication algorithms or replication protocols. So we need some tools to classify or understand the trade-offs involved in distributed data stores. And the most widely used tool is the CAP principle. It talks about three properties of a distributed data store: consistency, availability, and partition tolerance. And it says that we can have two out of these three properties. But in its essence, it basically says that we cannot achieve perfect consistency and perfect availability at the same time in the presence of network partitions. So network partition is a type of failure that causes the network to drop messages between servers, between our replicas, and it is always a possibility. So CAP is more like a CP versus AP decision, and if we choose CP, it means we lose availability on one side of the network partition, and we continue our operation on only the other side. By this way, we maintain our strong consistency. And on the other hand, if we choose AP, then we remain available on both sides of the network partition, so both sides can still operate on the data. And by this way, our data copies on different replicas can diverge from each other. So AP systems continue their operation with eventual consistency models. And the CAP principle talks about, I would like to add some more thing here. So there has been a huge amount of discussion about this principle, like it uses very narrow definitions, it's not very descriptive, or databases just don't fall into one category, etc. But still, it is quite useful for discussing where a product is aiming to be, especially when we focus on a particular use case of the product or maybe a particular feature of the product. And CAP talks about the consistency availability trade-off only in case of network partitions, but when we replicate a data set, another trade-off arises automatically. For instance, we can give up on consistency to reduce latency by talking to a closer but possibly a stale replica, or we can get extra latency while we are trying to maintain consistency of our replicas. So we have another principle, PACELC, to cover these two trade-offs together. So first, if there's a network partition in the system, we have to choose between availability and consistency. So this is the PAC part. It is same with CAP, just the letters are inversed. And else, when there is no network partition and the system runs under normal conditions, we can choose between latency and consistency. So this is the optional part. And I guess PACELC is not as popular as the CAP principle, but it is very useful for classifying distributed data stores. So from now on, we will build the core replication protocol of Hazelcast, so how we keep or how we maintain different copies of the same data. And then we will classify this protocol using these two principles, and we will also discuss what kind of problems we have in this protocol and how we can extend it or modify some of its parts to deal with these problems. Okay, let's start with thinking about on which replicas we should perform these operations, our operations. So one option is to elect a primary replica among our replicas. There are different namings for this approach, like primary backup, primary secondary, master slave, leader follower. We use primary backup terminology in our company, and I will just stick to that naming. So in this one, I have a single primary, and this primary replica orchestrates all the operations in the system. So operations are ordered on this primary replica and then replicated to the backup. So there are no concurrent operations or no conflicts on different replicas. And as long as we are able to talk to this primary, we get strong consistency because we always hit the most up-to-date version of our data. And the backup is mostly for fault tolerance. So in this approach, we favor or we choose consistency over latency because we always hit the primary for our data operations. And when the primary fails, we temporarily lose availability until we elect a new primary among the remaining replicas. And there is one minor problem in this approach because a primary can easily turn into a bottleneck because storage and throughput is limited by its capacity. And to overcome this problem, we apply another technique, partitioning, which is also called sharding. So in this one, we divide our key space into partitions and replicate each partition independently. And we also elect independent primaries for each partition. So in this simple example, I only have just three nodes, and I only have 3 partitions, P1, P2, and P3. And each node, each Hazelcast server becomes primary replica for one partition and backup replica for another partition. For instance, the node on the left-hand side is the primary for P1, which is the bold orange box, and it is the backup of partition 2, which is the blue box, normal blue box. So we have primaries to orchestrate operations among our replicas. So when it receives a write operation, now it should or it must replicate this operation to backups as well. So let's walk through an example to see how we do this in Hazelcast. So here I'm making a map.put call using an Hazelcast client. We have client implementations in many languages, including Java and other languages. So I'm just putting a key-value pair into a distributed map, that resides in a Hazelcast cluster. So first, the client internally calculates to which partition this operation should be sent by hashing the key and taking the modulo. Then forwards this operation to the primary replica of that partition. So this was the first step, and in the second step, this primary replica executes this operation locally. After this point, result of this operation is visible. So another client can read value of this key by talking to this primary replica. And in the third step, the primary replica sends this operation to the backup replica here. And in the meantime, it also sends the response back to the client. And in the final step, our backup replica executes this operation as well. And after our client receives a response for this operation from the primary, it can also optionally wait for an acknowledgement that will be sent by the backup replica. So this is a basic explanation of, this is a basic example of the async replication technique, because in this one, we update each replica with a separate transaction. Like, the primary does not guarantee that the backup will be the operation will be executed on the backup replica before the response is sent. They work in parallel. So this is why this is an example of async replication technique. So this technique is also called lazy replication or optimistic replication because of this approach. And it reduces coordination among different replicas of the same data. And by this way, it becomes a good fit for use cases like low latency, high availability, etc. But one result of this approach is our data copies are not guaranteed to be same state all the time. Due to some temporary problem like a network disconnection, our backup replica can miss some backup replication messages that is sent from the primary. Then it can diverge or fall behind the primary. And to resolve these issues, what we do is we run a periodic task on each Hazelcast server. So this task creates a summary information for the primary replicas it contains and sends this summary information to the backup replica nodes. And then each backup checks whether if its local data fits to or matches to the summary information that is sent from the primary. And if there is a mismatch, it triggers a synchronization with the primary to get the missing parts. So this technique is called active anti-entropy because it doesn't expect any explicit mechanism from the user, like an API call or a map or a get or put call. It just runs automatically in the background. So let's say that we are in this state. Again, I have the same example. I have 3 nodes, 3 Hazelcast servers, and I have 3 partitions. And I'm reading a value of a key from partition 1, from the primary replica of partition 1, which is the first node on the left-hand side. And let's say that its backup, which is the third node here, is not synced with the primary. So there were some lost backup objects earlier. So what we do is we get the current value of the key from the current primary replica. Then a network partition splits the third node and our client from the rest of the cluster. Now each side cannot communicate with the other side, and they assume that the other side is just gone. And this is a split brain situation. And in this case, my client sends the same GET request for the same key again. So I'm again trying to read value of the key, but this time I only talk to this single node here because I cannot communicate with the other nodes. So I have 2 options here. So we either refuse this third node to execute this operation and we lose availability. So this is one option. And in the other option, we allow this single node to elect its own primary replicas for these partitions and respond to the client. And in Hazelcast, we choose the second option. So what we do is this node promotes its backups to the primary role and executes this operation. And since one of the backups was not synced with the previous primary, it will send a stale response back to the client. And even if the backup was synced with the previous primary, This client can update this data entry on this side, and in the meantime, other clients can talk to the other part of the cluster, and they can also keep updating data entries, so data entries can converge during or diverge during network partitions, and we may lose strong consistency, and we may continue our operation with eventual consistency. So after some time, when the network problem is resolved, these subclusters discover each other, and this time the smaller side sends its data to the bigger side for merging, and we can use different merge strategies for this. For instance, if we have two different values for the same key, for instance, we can pick the one with higher number of hits, or we can pick the one with latest update time or latest access time, etc. Or we can write a custom function to merge these two values based on our application logic. And we should keep in mind that these strategies may not be 100% safe all the time. Because, for instance, if we use the latest update time strategy, we may lose the information in the discarded value, which has the lower timestamp or the smaller timestamp. So this is more or less the basic explanation of how the core protocol works under the hood. So now let's classify this protocol in terms of the principles we talked before. So I will just use the PACELC principle here because it already covers what the CAP theorem or the CAP principle talks about. So based on the PACELC principle, Hazelcast is PAEC. It means it is available during network partitions, and it is consistent during normal operation. But the thing is, consistency is usually traded to availability and latency together. For instance, in systems like Zookeeper, you maintain strong consistency for both during normal operation and network partition. So these systems are PCEC, consistent all the time. And on the other hand, when you give up on consistency, you favor latency during normal operation by making use of eventual consistency models, and you remain available during network partitions, like Dynamo-style databases. So these systems are PAEL. So our combination may look like an unorthodox design decision, but then we can justify it as following. So we use async replication to meet with the design goals of data grids. But since async replication can lead to eventual consistency in some failure scenarios, like we discussed in the previous part, we may have chosen to favor consistency by using eventual consistency for normal operation as well, but we don't do it. Achieving strong consistency or maintaining strong consistency requires either using a synchronous replication technique or having a primary copy, like we did in Hazelcast. But the thing is, Hazelcast works in memory, and it is also mostly used within a single computing cluster where our clients and servers are located in the same place. So latency-wise, it doesn't make a big difference to hit different servers or different Hazelcast nodes. So this consistency latency trade-off becomes minimal for normal operations. So therefore, we choose or we prefer to offer a better consistency model when the system runs under normal conditions. And this combination, PAEC, makes sense when availability is important and infrequent inconsistencies are acceptable, like distributed caching scenarios. So we allow our caches to be invalid for some time. But the thing is, since we cannot eliminate the possibility of inconsistency with this protocol, some applications may demand to give up on consistency a little bit more to get a better latency promise. And the source of consistency in our technique is the primary copy technique. We have a single primary for each data entry. So we can tweak this part, or we can play with this part to improve our latency promise. So let's see how we can do this for read-heavy use cases. For instance, we can reduce latency for the read-heavy use cases. So when a Hazelcast client reads a value of a key from an Hazelcast server, from a primary, it can put this value into a local cache, and after some time, if the same key is query it again, it can just serve the value from the local cache super fast. So in this technique, we reduce the latency of the system or the overall operations, read operations, but I lose strong consistency because now I'm serving the reads locally, and changes on my data on the Hazelcast server are asynchronously broadcast to the near caches in the clients. And the same idea also works when you use Hazelcast in the embedded mode. So in this mode, you can embed Hazelcast servers into your own application instances like microservices. And if an application instance contains a backup replica for some primary, for some partition, then it can just read values of the keys from this local replica. Then it will eliminate the remote call and reduce the latency. And we can also abandon the primary copy technique for both read and write operations. So the previous technique was only for reads. Now we can apply this to both reads and writes. There is a special technique, CRDTs, conflict-free replicated data types. So CRDTs have no primary replicas. You can read or write locally to any replica without coordination with other replicas. So by this way, you get low latency and high availability. It is okay as long as you are able to talk to a single replica. And it is mathematically proven that CRDT replicas will always make forward progress and converge to the same state. So this is called strong eventual consistency, and it's a very powerful consistency model. We can implement several data structures with this approach, like distributed counters, distributed sets, maps, graphs, etc. For instance, we introduced the CRDT counter in Hazelcast version 3.10, our latest version. So in this technique, we keep how many increments and decrements are made by each actor in the system, so that we will be able to calculate the final value of our distributed counter. In our solution, these actors are a subset of Hazelcast servers that will behave as CRDT replicas. For instance, one of my clients sends an increment operation to replica A, and the other client sends a decrement operation to replica B. And these replicas just execute these operations and return responses back to the clients. Now, value of my counter is 1 on replica A and -1 on replica B. So here it is +1 and here it is -1. Because node B only knows that there was only one decrement operation, and node A only knows that there was only one increment operation. Then in the background, these replicas propagate their state to each other and then merge their state. So final value of my counter becomes 0 in both replicas, because now each replica notices that there is only one increment and another decrement. So more or less, this is how our CRDT counter implementation works under the hood. And we are planning to add more CRDT data structures in future releases. And I think this can be quite useful when you embed Hazelcast servers into your application instances, because your application instances can behave like CRDT replicas. You can perform your reads and writes locally with very low latency, and still you will get a very useful consistency model. So okay, this was all about how we can tune the system to improve latency of our operations, and some other applications may also require to get a better consistency promise by Hazelcast. So let's see how we can do this. I would like to talk about an interesting case where we improved consistency of our system by abandoning the primary copy technique. We have a feature called ID generator to generate cluster-wide 64-bit unique IDs. So this feature basically works like this. When you want to generate a unique ID, you first fetch an ID block from a primary replica. Then you generate all the IDs within this block, and then once you consume this block, you get another block from the same primary again. But because of the async replication under the hood, the same ID block can be assigned to multiple nodes in case of some failure scenarios. And this time, this unique ID generation mechanism breaks, so duplicate IDs can be generated. And we resolved this problem by developing a new feature, Flake ID generator. So this time, each node or each Hazelcast server has a local ID generator. And Hazelcast's cluster join algorithm assigns unique IDs to each node during the join process. You know, when you start a new Hazelcast server, it first joins to the cluster, and in the meantime, it gets a unique integer node ID. And then we embed these integer IDs to our Flake IDs here, and we also put a timestamp component. So generated IDs are roughly ordered by generation time, depending on accuracy of the clocks on the servers. And we get rid of the remote call to the primary replica, and with using unique node IDs, or by embedding unique node IDs into our generated IDs, we get rid of the duplicate ID generation issue. And another idea or another technique to improve consistency of the system is to make use of failure detectors. So each Hazelcast node has a failure detector here, and nodes send periodic heartbeats to each other, and these local failure detectors keep track of these heartbeats to make suspicions about other nodes in the system. And the idea is, if we allow a primary replica to execute operations only if size of the cluster reported by the failure detector is bigger than half of size of the cluster, then we can execute this operation. Otherwise, we just reject it. For instance, so this is basically the majority quorum idea, and it is also used in other systems like Cassandra and many other tools. So here I have a 3-node cluster, and my threshold is 2. So if the cluster splits like this, like in this previous example, the bigger site will execute or will continue executing the operations because it still reports a cluster size bigger than 2. So it is 2, and in the other side, the single node will stop executing these operations because its cluster size falls below our threshold, which was 2. So this is a useful idea, but it has a shortcoming. The thing is, this little node still executes operations after the cluster split until it eventually detects that the other 2 nodes are gone or has become unreachable, because it doesn't stop executing the operations exactly when the network split occurs, because failure detection takes some time, and in the meantime it still executes these operations. So this technique does not result in a strongly consistent system, but it minimizes divergence, because divergence can occur only in the beginning of the network partition until the failure detection mechanism kicks in. So we say that this approach maintains the baseline consistency because it tries to minimize the divergence window, and it is still considered as a consistency-oriented approach. And before Hazelcast version 3.9, we only had a single failure detector implementation, which is deadline-based. So if you don't hear any heartbeat from some node for like 5 minutes, just assume that the other node is gone. And in 3.9, we introduced a new probabilistic failure detector, phi accrual failure detector, which is also used in other tools like Akka and some other tools. And it helps us to make faster failure detections by adjusting accuracy. And in Hazelcast version 3.10, we also enabled different data structures to configure their own failure detectors. For instance, if you have a distributed map or cache that contains some data which is more critical compared to the others, you can adjust a more aggressive failure detector, like assume other nodes are gone if you don't hear any heartbeats for 5 seconds. So you can tune such a configuration, and by this way you will minimize the window of divergence to a smaller period with the cost of possibly more false positives in case of hiccups in the system, because If another node hits a GC that takes more than 5 seconds, then you can assume that the other node was gone, although it was alive. But the other data structures in the system will not be affected from this configuration. So this is the useful part. So you can isolate failure detection mechanisms if you have heterogeneous data sets in the cluster, or data sets with different characteristics, different importance values, etc. We also, besides distributed data structures that can keep large amounts of data in a cluster, we also have some concurrency primitives. We implement distributed implementations. We offer distributed implementations of Java concurrency APIs like logs, semaphores, atomic longs, atomic references, etc. And this failure detector approach does not work well for these data structures. For instance, a distributed log that can be acquired on both sides of a network partition, or an atomic long that can be atomically incremented on both sides of a network partition, these are not very useful, or they are not even correct. And majority-based consensus algorithms like Paxos, Raft, Zookeeper atomic broadcast, or weave-stamp replication employ synchronous replication techniques to maintain strong consistency. They guarantee that an operation is executed only after it is committed to majority of the cluster. Therefore, they always maintain strong consistency. Raft is one of these algorithms. It is relatively a new one, and it builds a simple and easy to understand solution to solve this problem, to offer a strongly consistent system. And what we do is we have been fixing our concurrency primitives by re-implementing them on top of the Raft algorithm. So we first implemented the Raft algorithm itself within our code base, then now currently we are re-implementing our log implementation, atomic long implementation, and the other data structures, this concurrency related data structures on top of the Raft algorithm. Therefore, we will be able to serve a CP solution, always consistent solution for these concurrency primitives. So I can say that we have made, this is still work in progress, but we have made some good progress, so I'm quite hopeful for the possible outcomes. So okay, I've talked about a bunch of stuff. I would like to recap what we discussed. So data grids are elastic solutions that offer low latency and high availability. And in order to meet with these design goals, Hazelcast uses async replication and remains available under network partitions. But this solution or this approach can lead to eventual consistency. But still, we prefer to offer strong consistency during normal operation because we can do it with a minimal consistency latency trade-off. And we believe that, or we think that this is a very useful model for data grid use cases like distributed caching. And we have an extensive documentation page that explains all of this stuff in detail in order to make everything clear for developers. It is just a section in our official reference manual. And we have been also putting a huge amount of effort into these parts. Like, we implemented near caches and CRDTs to improve the latency promise of the system. And we also resolved the duplicate ID generation problem by implementing a new data structure, Flake IDs. We also improved our failure detection mechanisms to minimize divergence in case of network partitions. If you don't want to go for fully eventually consistent system. And we are also fixing our concurrency primitives like logs, atomic longs, etc. by implementing them on top of a consensus algorithm. So that's all for my talk. I hope you enjoyed this session. I would like to thank the conference organizers for having me here. This is the first time I give this talk in a public conference, so this is a good experience for me. If you have any feedback, I would like to hear it. You can just find me via Twitter or my email. And thank you. That's all.